today's CPUs can contain over 90 billion transistors, each smaller than a virus particle, yet powerful enough to execute billions of calculations every second? Often called the brain of a computer, the Central Processing Unit, CPU, processes instructions, performs calculations, and manages virtually all data flow within a computer system. Companies like Intel and AMD produce CPUs so advanced that a single chip, smaller than your fingernail, is more powerful than the supercomputers that first sent astronauts to the moon. Today, join Captain Discovery on an exciting adventure into the heart of technology as we explore how CPUs, the powerful brains of our computers, are made and how they work. From incredible clean rooms larger than football fields to microscopic transistors thousands of times smaller than a human hair, we'll uncover each fascinating step behind creating these tiny yet mighty chips. And don't forget to like and subscribe to Captain Discovery. The history of CPUs began when Intel created the first microprocessor, the Intel 4004, in 1971, and this breakthrough opened the door for smaller, powerful computers. Soon after, Intel released the 8086 chip, which became the foundation for IBM's first personal computer in 1981, transforming the computing industry. Throughout the 1980s, Intel continued improving CPUs by launching the 80286 and 80386 processors, which offered better speed and multitasking abilities. IBM, meanwhile, expanded their personal computer market by utilizing these advanced chips, making PCs more affordable and accessible. In the 1990s, Intel introduced the Pentium processor, significantly boosting computing performance with advanced multimedia capabilities. IBM competed by developing the PowerPC architecture in partnership with Motorola and Apple, aiming to challenge Intel's dominance. Since the 2000s, Intel has advanced CPU technology with core processors featuring higher efficiency and reduced power consumption. Although IBM shifted its focus away from personal computers, the company still innovates with high-performance chips for supercomputers and servers. The CPU manufacturing process starts with refining quartzite into extremely pure silicon through intense heating and chemical purification. This silicon achieves an incredible purity level of 99.9999999%, known as 9N purity. Next, the purified silicon is melted and carefully grown into a cylindrical crystal called an ingot, which can weigh over 100 kilograms. These ingots are sliced into thin silicon wafers, typically 300 millimeters in diameter, each around 0.75 millimeters thick, thinner than a credit card. A single wafer costs about $100 initially, but after processing and populating it with CPUs, companies like Intel can increase its value dramatically, up to $100,000 per wafer, making it significantly more valuable by weight than gold. Next, the wafer is coated evenly with a thin, light-sensitive material called photoresist, spun onto its surface at high speeds. Ultraviolet, UV light, shines through precise stencils known as photomasks, imprinting microscopic circuit patterns onto the wafer's surface. This crucial step is repeated around 80 times per CPU chip, each photomask costing companies like Intel approximately $300,000, highlighting how expensive and critical this step is to CPU manufacturing. The patterns created are extremely small, measuring just a few nanometers, thousands of times thinner than a human hair. If you find this video interesting, don't forget to subscribe to Captain Discovery. In this stage, the wafer undergoes a precise chemical or plasma etching process, removing silicon material only from areas unprotected by the photolithography mask, forming microscopic channels and structures. Next, these tiny etched channels are filled by depositing ultra-thin layers of materials such as copper, silicon dioxide, and other insulating oxides. Intel uses advanced deposition tools that add metal layers so thin, just a few nanometers, that thousands would fit inside the thickness of a sheet of paper. Each completed layer of metal and insulating materials creates the intricate wiring needed to interconnect billions of microscopic transistors inside the CPU. After completing a single patterned layer, the wafer returns repeatedly to photolithography, etching, and deposition tools, with each CPU chip requiring about 80 intricate layers, totaling around 940 individual manufacturing steps. Throughout this lengthy process, semiconductor factories such as Intel and TSMC continually clean and inspect wafers to eliminate dust particles, because even a microscopic speck can ruin an entire chip. Metrology tools, including powerful electron microscopes capable of inspecting features smaller than a virus particle, ensure each layer is accurately formed, maintaining precision within just a few nanometers. In this critical step, ion implanters precisely shoot atoms such as boron or phosphorus into specific silicon regions on the wafer, changing the silicon's electrical properties to form transistor channels. The atoms are implanted at extreme speeds, similar to firing baseballs into a concrete wall, to penetrate deeply into the silicon lattice. Because this process slightly damages the silicon structure, wafers then undergo an annealing process, heating them carefully to around 1000 degrees Celsius, restoring the crystal structure and ensuring stable electrical behavior. Companies like Intel utilize ion implantation to create transistors smaller than 10 nanometers, packing billions of these precisely engineered structures onto each CPU chip. Once the wafer has completed its extensive, months-long manufacturing journey, each CPU undergoes a thorough final inspection to ensure functionality, with advanced testing equipment identifying even microscopic defects. Intel reports that some wafers inevitably contain defective chips due to minuscule imperfections. These partially functional chips are carefully categorized, bin, based on their working cores and performance capabilities, becoming different product lines such as Core i9, i7, or i5. After inspection, powerful lasers precisely cut the wafer into hundreds of individual CPU chips, each carefully separated for packaging and assembly, preparing them for their eventual installation into electronic devices. In this step, each CPU chip is carefully placed onto a small substrate known as an interposer, which connects microscopic chip contacts to larger circuit boards and allows easier integration into computers. A protective metal cover, known as an integrated heat spreader, IHS, is attached on top to distribute heat generated by billions of active transistors during operation. After assembly, each CPU undergoes rigorous final testing to verify reliability, stability, and peak performance. For example, Intel individually tests every CPU under heavy workloads to ensure flawless functionality before packaging. Only after passing these demanding quality checks are the CPUs packaged securely and shipped worldwide, ready for installation into desktop computers, laptops, and other electronic devices. Data centers, cars, and every single iPhone all rely on one crucial component: microchips. As technology advances, scientists and startups worldwide are working on developing low-energy microchips that use less power while delivering even greater performance. Today, Captain Discovery takes you inside the ASML factory to uncover the incredible process of how microchips are made, one of the most complex and advanced manufacturing feats in the world. And if you're curious about why Apple relies on TSMC to produce its powerful chips, Stick with us until the end of the video. Microchips were first developed in the mid-20th century, revolutionizing how computers, phones, and other devices function. In this section, we will give you the brief history of three biggest manufacturers in the chip market: Intel, TSMC, and ASML. Let's start with Intel. This company, founded in 1968 by Robert Noyce and Gordon Moore, was one of the first companies to develop microprocessors, which act as the brain of computers. Over the years, Intel has continued to innovate, producing powerful chips like the Pentium, Core i series, and Xeon processors, which drive everything from personal computers to data centers. And TSMC, founded in 1987 by Morris Chang, became the world's first dedicated semiconductor foundry. Unlike companies that design and manufacture their own chips, TSMC focused only on producing chips for other businesses, allowing it to work with major tech giants like Apple, Nvidia, and AMD. The last, ASML, founded in 1984 in the Netherlands and has become the world's leading supplier of lithography machines, which are essential for making microchips. This company is the only company in the world capable of producing extreme ultraviolet EUV lithography, a cutting-edge process that uses extremely short wavelengths of light to create the most advanced chips. Microchips start with silicon, a natural element found in sand and quartz. Since silicon is a semiconductor, it is the perfect material for controlling electrical signals in electronic devices. The sand is heated to extremely high temperatures, about 1,700 degrees Celsius, causing the oxygen to separate from the silicon. To achieve the ultra-high purity, the silicon undergoes chemical refining in a process called the Siemens process. The purified silicon is melted in a high-temperature furnace and then formed into a large, cylindrical silicon ingot. A small seed crystal of silicon is dipped into the molten silicon and slowly pulled upward while rotating. The resulting monocrystalline silicon ingot can be up to 300 millimeters in diameter, the standard size for advanced semiconductor manufacturing. Now, the silicon ingot is cut into ultra-thin wafers about 0.5 to 1 millimeter thick, using diamond-tipped saws. Each silicon wafer is polished to a mirror-like finish, because even a single dust particle could ruin the delicate circuit patterns. Now, engineers use specialized software to design the layout of the microchip circuits. Modern microchips can contain billions of transistors, which must be strategically placed to ensure fast processing and minimal energy consumption. Because microchips are too small to be physically drawn, engineers create a photomask. This is a high-precision glass plate coated with a light-sensitive material that contains an etched image of the chip's circuit design, the blueprint for the circuit pattern. The mask is used in the lithography process to project the intricate chip design onto the silicon wafer. Modern chips use extreme ultraviolet lithography, EUV, a process that prints features as small as 2 to 5 nanometers, which is more than 10,000 times thinner than a human hair. The photomask reduces the circuit design to an atomic-level scale, allowing billions of transistors to fit onto a single chip. And, since microchips are made up of multiple layers, multiple photomasks are created for different circuit layers. Each layer contains a specific part of the circuit, such as logic gates, memory cells, and electrical connections. This will explain why the chip can perform millions of calculations per second. The finalized photomask is sent to the fabrication plant, where lithography machines will use it to print the circuit patterns onto silicon wafers. And if you like this content, subscribe to Captain Discovery now. Now that the circuit design is complete and the photomask is ready, the next step is lithography, a process where precise light beams print the microscopic transistor patterns onto the silicon wafer. The wafer is spun rapidly, which can up to 5,000 RPM to make sure the photoresist spreads evenly across its surface, creating a thin and smooth layer. The wafer is placed inside a high-tech lithography machine. Then, a powerful laser beam passes through the photomask. It will then treat it with a developer solution, which removes either the exposed or unexposed areas of the photoresist. Since microchips have multiple layers, this process is repeated multiple times for each layer of transistors and electrical pathways. Once the lithography step is complete, the wafer moves on to etching, doping, and metal layering, where the transistors and circuits are physically built into the silicon. There are two main types of etching. One is wet etching, uses liquid chemicals to dissolve unwanted material. Second is dry etching, which uses high-energy ionized gas to remove material at a more precise atomic level. This step clears away unnecessary silicon, creating tiny trenches and holes where transistors and connections will be formed. Next, the silicon wafer undergoes ion implantation, also known as doping. This process adds small amounts of other elements into the silicon, changing its electrical properties and allowing it to function as a semiconductor. High-energy ion beams shoot these elements into specific regions, helping form the chip's logic gates and memory cells. Once the transistors are in place, insulating materials are deposited onto the wafer to separate different layers of the circuit. The wafer then goes through metal deposition, where copper or aluminum layers are added to form electrical connections between transistors. These metal layers are applied using a process called sputtering, or electroplating, ensuring high-speed electrical conductivity. After multiple layers are deposited, the wafer surface must be smoothed and flattened to prevent defects. This is done by a process called chemical-mechanical planarization to polish the wafer surface. Now that the microchip's transistors and circuits have been fully built, the final step is testing, cutting, and packaging. Some tests include thermal testing, exposing chips to extreme heat and cold to see if they function under harsh conditions. Stress testing, simulating real-world use cases to detect any potential failures. Power efficiency testing, ensuring the chip consumes minimal energy while performing at high speeds. protect the delicate microchip, it is encased in a durable plastic, ceramic, or metal shell. Modern chips use advanced packaging techniques like 3D stacking, where multiple chips are layered on top of each other for higher performance and lower energy consumption. After passing all tests, the finished microchips are shipped to electronics companies, where they are installed in smartphones, computers, gaming consoles, self-driving cars, medical devices, and even space equipment.
Have you ever wondered how your familiar laptop is created? From a small circuit board to a powerful machine, every step in the process is a masterpiece of precision and ingenuity. Today, Captain Discovery will take you deep inside a laptop factory, where even the smallest details are assembled to create a perfect product. Be sure to watch the video until the end to explore the entire production process. And don't forget to hit like to support Captain Discovery in bringing more exciting content. Let's get started. The first portable computer appeared in the 1980s. In 1981, the Osborne 1 was launched, and it is regarded as the first commercially available laptop. In the years that followed, companies like Compaq and IBM quickly refined designs, introducing lighter and more powerful models. By the 1990s, laptops gained significant attention as technologies like lithium-ion batteries and LCD screens made them thinner, lighter, and longer lasting. This era also saw the introduction of iconic designs like the IBM ThinkPad with its distinctive track point. Entering the 21st century, laptops saw unprecedented development with the launch of ultra-thin, ultra-light, and multifunctional devices like Apple's MacBook Air and powerful gaming machines like Alienware. Today, laptops are not only tools for work, but also gateways for entertainment, learning, and even a reflection of modern lifestyles. So, how are laptops made? Do you know what connects and controls all the components in a laptop? It's the motherboard, the brain of the computer. The process begins with a printed circuit board. Robots place a stencil component layout onto the board and apply solder paste through its openings. This step sets the foundation for connecting electronic components. A quality control camera photographs the solder paste and sends the images to a computer for analysis. The computer meticulously checks for issues like missing or misaligned solder. If the board passes inspection, it moves to a robotic assembly line. Here, 15 robots work simultaneously, placing up to 150 components onto the board in just 30 seconds. The board is then sent through an oven, which melts the solder paste to secure the components. Finally, a camera checks if all components are soldered correctly and ensures that none are missing or misaligned. Once everything meets the required standards, the motherboard is ready for the next assembly stage. After the motherboard is ready, what part comes next? It's the screen, the display for all the images and information you see. Technicians start by applying a protective film to the LCD screen. Next, they carefully connect cables between the screen and the motherboard. The screen is mounted into a frame that includes a built-in webcam and microphone, then finished with a thin metal bezel for added durability and aesthetics. With these details in place, the laptop screen is ready. Now that the screen is complete, the laptop still isn't functional. So, what's next? The bottom half of the machine, home to key components like speakers, the keyboard, and the motherboard. First, technicians attach the touchpad and speakers to the frame. Next, the motherboard, which has already been inspected thoroughly, is placed into position. For gaming laptops, engineers add 2 large fans for cooling, as these machines generate significant heat during operation. After checking that the fan screws are properly tightened, the motherboard is placed into the top cover. Memory module connectors are cleaned with solvent and dried with compressed air to ensure proper contact. The memory modules, Wi-Fi, Bluetooth, and SSD storage are then installed. A large battery is connected to the motherboard to meet the higher power demands of gaming laptops. Finally, the keyboard is fitted into a rectangular opening on the top cover, and laser etching machine completes the required information underneath. The laptop is now nearly ready. Have you ever wondered how laptops are tested to ensure they work perfectly before reaching you? After assembly, every laptop undergoes a series of strict quality checks. Automated machines test functions such as the display, keyboard, and cooling system. Meanwhile, technicians manually check additional features like screen color accuracy, keyboard durability, and overall build quality. These tests ensure that every laptop is perfect for users. Now the laptop is complete, but before it reaches consumers, it must be carefully packaged. Technicians clean the laptop, package it with accessories such as chargers and cables, and ensure it is ready for safe shipping. The laptops are then transported to stores worldwide, ready to serve users. To minimize environmental impact, many laptop factories have adopted solar energy in their operations. Solar panels installed at manufacturing sites provide clean, sustainable electricity, significantly reducing carbon emissions. Which brand of laptop are you using? And how does it perform? Share your experience in the comments below. If you found this video interesting, don't forget to subscribe to Captain Discovery for more fascinating content in the future.